expected normal resistance reading for the leads, there is no ground present. A reading of 0 or nearly 0 indicates that there's a ground somewhere in the motor. In order to determine exactly which part or parts are grounded, further tests must be made using the process of elimination. In other words, one circuit at a time must be tested to eliminate those that are not grounded. For example, the compound motor represented by this diagram has 3 separate circuits: the series field, the shunt field, and the armature. Each circuit must be tested individually, and then each part in any grounded circuit must be tested separately. First, the electrician raises the brushes off of the armature to separate the 3 circuits. Then he uses the meg ohm meter to test each circuit separately. To test the series field, the electrician attaches the meter's ground lead to the motor's metal frame, and the meter's line lead to the S lead. When the electrician operates the meter to make the test, it shows a normal resistance reading for the series field. This means that the entire series field can be eliminated. There are no grounds in this circuit. To test the shunt field, the electrician moves the meter's line lead to the F lead. The meter's ground lead remains attached to the motor's metal frame. When the electrician operates the meter for this test, it shows a reading of almost 0 resistance. The next step is to test the armature. To do this, the electrician attaches the meter's ground lead to the shaft of the motor and holds the meter's line lead against the commutator. The electrician then operates the meter, and this time it indicates a normal resistance reading for the armature. There is no ground in the armature circuit, so the entire armature assembly can be eliminated. At this point, both the series field and the armature have been eliminated from consideration, and troubleshooting is focused on the shunt field. The next step is for the electrician to disassemble the motor and find out where the ground is in the shunt field. After the motor is disassembled, the connections between the field coils can be broken, and each coil can be tested individually. Any bad coils that are found can be replaced, and then the motor can be reassembled, tested, and returned to service. Now, another common problem that can be found in a DC motor is an open. An open is a break that stops current flow somewhere in a circuit. To check for opens in a DC motor, the motor is de-energized, locked out and tagged, and then each circuit is tested individually from end to end with an ohm meter or a multimeter that's set to measure resistance. For example, this compound motor diagram shows 2 paths for current flow: a shunt field circuit and a series field circuit. To separate these 2 circuits and the armature circuit, the motor's brushes are lifted off of the commutator. We'll test the shunt field circuit first. According to the diagram, the shunt field must be read from motor lead F1 to motor lead F2. On the diagram, the F1 lead is also marked A1 for the armature circuit, but this is not a problem because the armature circuit was disconnected when the brushes were lifted off of the commutator. So, to test the shunt field, one ohm meter lead is connected to motor lead F1, and the other ohm meter lead is connected to motor lead F2. We'll say that the ohm meter indicates very low resistance, which means that there is no open in this circuit. A high resistance reading would have indicated an open in the circuit. The series field is checked next. According to the diagram, the series leads are S1 and S2. The diagram also indicates that S1 is connected to the brushes, but it does not indicate which brush, the negative brush or the positive brush. To determine which brush is connected to S1, one of the ohm meter's leads is connected to S2, and the other lead is connected to a lead connection on one of the brush holders. We'll say that the meter does not show a reading, so either there is an open in the series field, or the meter lead is connected to the wrong brush holder. To check further, the meter lead is moved to the other brush holder. Now we'll say that the meter indicates a low resistance reading, so the second brush holder is the right one, and the series field is not open. At this point, it has been determined that there is no open in the series field circuit, and there is no open in the shunt field circuit. However, the series field has only been eliminated as far as the brushes, so the next step is to check the brushes. To check a brush, 1 ohm meter lead is placed on the brush pigtail, and the other lead is placed on the commutator segment directly under the brush. If there is a reading, the brush is all right. If there is no reading, there is an open. In this case, we'll say that there is a reading, so this brush is all right. The same check is then repeated for the other brush. This time, we'll say that there is no reading, so this brush is faulty. A detailed check is then performed on the faulty brush and on the commutator. The brush is removed, and the brush's pigtail, the brush length, the brush's contact surface, the inside of the holder, and the bottom of the holder are all examined. In this example, the brush has worn down and it's too short. Then the commutator is inspected for dirt, contaminants, and general color. In this case, the commutator looks all right. Since the brush is too short, it is replaced with a brush of the proper size and grade. After the brush has been properly seated, it is tested. In this case, the ohm meter shows a reading, so the new brush is all right. The next step is to test the entire circuit that includes the series field, the armature, and the brushes to see if the open has been repaired. We can use the diagram to identify a current path that allows this to be done. The shunt field has already checked out all right, so it can be bypassed. So, according to the diagram, 1 meter lead should be placed on motor lead F1A1, and the other lead should be placed on motor lead S2. The current path being tested is from motor lead S2 through the series field to S1A2, through the brush, through the armature and the other brush, to F1A1. If the meter shows a reading, we'll know that the series field, the armature, and the brushes are good, and that the problem has been solved. The last motor problem we'll look at is a short. A short occurs when there is minimum resistance through a component and maximum current flow. The excess current generates heat in the component, and it may also cause a motor to smoke. Usually a short will cause fuses to blow or circuit breakers to trip. Evidence of a short in a motor is usually found in the condition of the insulation. For example, the insulation may be hot to the touch, it may be charred, or it may crumble when it's touched. If a motor has started to smoke, or if it has blown a fuse or tripped a circuit breaker, it's a good idea to check the motor for grounds. This is because shorted coils in a motor are likely to ground. If the test for grounds doesn't indicate that a ground exists, then you should look for a short. You can do this by testing for opens because shorts rapidly become open circuits. Take a moment now to check your knowledge of troubleshooting DC motors. In this part, we'll see how a DC motor can be disassembled for maintenance. When overhauls are required, DC motors are stopped, de-energized, and locked out and tagged according to approved procedures, and in many cases, moved to a workshop. Work area preparations may include spreading a cloth on which to place the motor. The first step in disassembling a DC motor is to lift up or completely remove the inspection covers on the motor end bell to gain access to the brush rigging. Next, the pigtail bolts are loosened, and then the pigtails are slipped out of the bolts. The brush tensioning assemblies are then released, and the brushes are removed. As they're removed, it's a good idea to place them in a separate container to protect them from damage. The field coil leads are then removed from the brush rigging. The end bells are removed next, after they're marked to ensure that they will be put back in the right place. You may hear these marks called witness marks or registration marks. In this example, the end bell and frame at the drive end of the motor is marked with the letter IB for inboard, and the other end bell and frame at the other end is marked with the letters OB for outboard. After the end bells have been marked, a wrench can be used to remove the seal bolts for the bearings, and then the end bell bolts. The bolts are placed in a parts pan or other container to keep them safe. Then the end bells can be removed from the motor frame. One end bell contains the brush rigging, so it must be removed carefully to make sure that it does not cause the brush rigging to damage the commutator. The next step is to remove the armature. Keep in mind that once the end bells are removed, the armature is resting on the motor's field poles. If the armature is dragged across the field pole pieces, it could damage the armature and the field pole pieces. The armature should be lifted, moved carefully out of the frame, and set down on a cloth or V-blocks, or, as in this example, in a pair of stands. This completes the disassembly of the motor, unless your company's procedures require the motor's bearings to be removed as part of an overhaul. If the bearings have to be removed, a bearing puller may be used. Take a moment now to check your understanding of what's involved in disassembling a DC motor. In this part, we'll look at how a disassembled DC motor can be inspected and cleaned. After the motor has been completely disassembled, the next step is to give each of the parts a thorough inspection. The parts of the armature are easier to inspect if the armature is placed in a set of V-blocks or in a pair of stands. A dial indicator can be used to check the commutator for trueness. In other words, to make sure that all of the segments are level with each other. Each segment is numbered to identify them, and then checked with the indicator actually on each segment. The armature should be rotated very slowly, and the readings should be recorded accurately. As a general rule, if the difference between individual commutator segments exceeds 0.002 inches, the commutator must be machined or ground. Next, the armature winding should be checked to make sure that there is no evidence of solder being thrown out of the risers. The presence of solder is usually an indication that the commutator has been overheating, either because of a motor overload or because there is armature winding damage. The area behind the risers should be checked to make sure that there is no melted solder, dirt, or carbon dust there. If any foreign particles are found, they should be removed with an approved cleaning solvent, rags,